Hey, advanced geometry students, it's Mr. Donaldson here, and today we're going to talk about section 5.3, which focuses on properties of kites and trapezoids. Um, you may remember back in chapter 1, I think it was section 1.6, where we introduced to you the definitions of kites and trapezoids and a rhombus and a rectangle and a square and all these things. But that's all we said was, hey, here are the definitions, and then we moved on. Just introduced these ideas to you. So today's focus is going to be, okay, now that we know those definitions from chapter 1, and also now that we know how to prove triangles are congruent, we can take those two ideas and together we can justify special properties that are true about kites and trapezoids. So, first, a reminder of the definition. A kite is a quadrilateral with exactly two distinct pairs of congruent consecutive sides. Now, distinct means different. That means these pairs of congruent sides can't all be the same. So if these sides were like 5, these could not be 5. Because if all the sides were the same, it would then be a rhombus. That's what distinct means, is different. Okay, so maybe these would be 8 or something. All right, and then consecutive congruent sides means the sides that touch each other or next to each other are the ones that are congruent. All right, so just important kind of the wording of the definition is important. Now, in a kite, we've got some parts that you got to be able to identify. So the first is called the vertex angles. The vertex angles of the kite are just like the vertex angles of isosceles triangles. And the easiest way to think about that is if I draw this horizontal line and cut this kite into two isosceles triangles, if I said, what's the vertex angle of this top triangle? You should know the vertex angle is the angle that's formed by the congruent sides. So this angle up here would be a vertex angle. And the same would be true for this one down here. So vertex angles are the angles formed by the pairs of congruent sides. So in this diagram, that'd be angle I and angle E. And then if those are the vertex angles, not so scientific, we call the other ones non-vertex angles. That'd be angle K and angle T. And there the angle is formed by the non-congruent sides. So it's really important if I give you a problem and say you kite A, B, C, D, E with vertex angles A and C. All right? Or whatever I say. You got to understand how to draw it and know which part is which. So make sure you pay close attention to vertex angles are the angles between the congruent sides, and non-vertex angles are the angles between the non-congruent sides. So we're going to learn some theorems about kites. Now, before we talk about these theorems and write them down and kind of what they mean, I think it's easiest for us to visualize, well, what makes a kite a kite? And the easiest way for me to give you a visual representation of how to remember these properties is, you guys, the easiest thing is that a kite is symmetrical. So if I had a triangle and I cut it out on a sheet of paper, like let's say I folded a sheet of paper in half, cut out a triangle and then unfolded it, I would get a kite. All right? And if you can just picture the symmetry of a kite, you'll remember all of these different theorems. So if that's true, if I unfold this and the right and the left side are exactly the same in every way, which you'll notice they are congruent triangles because of side, side, and then shared side, side. These two triangles are congruent, so everything on the left must be congruent to everything on the right. So what that means is this. This vertical diagonal in this picture, diagonal BD, it would bisect the vertex angles. So this little half over here will be congruent to this little half over here. All right? Same would be true on the bottom. And also you'll notice these non-vertex angles have to be exactly the same. Right? If I fold this on top and unfold it, angle A was 80 degrees, and angle C would have to be 80 degrees. All right, now let's draw this second diagonal. Now again, same deal. If this is just symmetrical of the other one, then you'll notice that AE would have to be congruent to EC. And also, if these two angles add up to 180, because they're a linear pair, but they must be the same because of that symmetry we just discussed, well, that means they got to be 90. So what that means is that these segments are congruent, and this is a right angle, or these lines are perpendicular to one another. All right? So just by seeing this symmetry, you can kind of see all these little theorems that are true about a kite. So here are the theorems about a kite. First, the non-vertex angles are congruent. So what that would mean in this picture over here is that angle IKE would have to be congruent. Angle IKE, this whole angle, would have to be congruent to angle ITE because of that symmetry. All right, next, the diagonals must be perpendicular. And I just showed that to you with my little sketch. The diagonals must be perpendicular to one another. So that means that segment IE would have to be perpendicular to segment KT. And each one of these little angles would be right angles or 90 degrees. All right. The other thing when we mentioned is that this part of the diagonal is equal to this part, or congruent, this part of the diagonal. What that means is that this diagonal, the vertex angle diagonal, IE, is called a perpendicular bisector of the other diagonal. Perpendicular, because it forms a right angle, and bisector, because it goes through the midpoint of that other diagonal. So because of this theorem, there's two things I know. Let's call this point M. I would know that M is the midpoint of segment KT. And I would also know that segment IE, just like this is a little bit redundant from the one above, is perpendicular to segment KT. Perpendicular bisector means both of those things. It means perpendicular, and bisect means go through the midpoint. And then the last little theorem here, based on that symmetry, if we go back and look, is that when I unfold this left side angle has to be congruent to that right side angle, which makes this diagonal an angle bisector. And that's that last thing. It says the vertex angles of a kite are bisected by the diagonal. So that means ray IE must bisect angle KIT, and ray EI must bisect angle KET. Oops. KET. There we have it. These little angles would be the same, and these little angles would be the same. So that's all true about kites. All right, so the next thing in today's lesson is isosceles trapezoids. All right. Oh, but before we get there, oops, I forgot. I was going to show you justification of just how you would kind of quickly and informally prove one of these theorems. Check it out. Prove the following theorem. I want to prove the non-vertex angles of a kite are congruent. So the given is that I have a kite, but I got to be a bit more specific, okay? So the given is I have kite A, B, C, D, but I got to tell you which sides are congruent or which angles are vertex angles, or some more information so you know which parts are which. So maybe I'll say with non-vertex angles, angle D and angle B. Those are my non-vertex angles. I want to prove they got to be congruent. All right, check this out. First things first, I got a kite. So kite A, B, C, D. Well, by the definition of a kite, that means that these two segments must be congruent, and these two segments must be congruent. And the reason I knew that those were the congruent pairs is because if D is a non-vertex angle, it's between two different side lengths. Same for B. So if this is a kite, that means that AD must be congruent to AB, because the definition of a kite, and by the same reasoning, DC must be congruent to BC. Again, that's because the definition of a kite. Kite has those pairs of congruent sides. All right, the other thing we're going to do in order to prove this is, remember, everything that we do from here on out is going to build on all that stuff we just learned about congruent triangles. Well, I don't have triangles right here, but if I draw this segment, which is going to be not super straight, segment AC, and I could draw a segment between 2 points because it exists, I could say that AC is congruent to itself because it's a shared side. And so these two triangles are congruent. So triangle ADC is congruent to triangle ABC. And the reason for that is by side, side, side. And if those triangles are congruent, then their corresponding parts are congruent by CPCTC, which means angle D would have to be congruent to angle B. And you guys, this is the reason we stressed and spent so much time on congruency for triangles, because all these other ideas we're going to learn in geometry are built on that concept of congruent triangles. Well, if triangles are congruent by side, 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 I could justify angle D has got to be congruent to angle B. I could also justify that this little angle is congruent to this one, and this one congruent to this one, which was that other theorem about the angle bisector. All right, next is a trapezoid. So a trapezoid is a quadrilateral with exactly one pair of parallel sides. So we'd say like TR is parallel to PA. Those two sides are called bases. The bases are the parallel sides. So segment TR and segment PA. The base angles, all right? And I probably should have put legs on here. Legs are the non-bases. And in this case, that'd be like TP and RA. And base angles are the pair of angles that share a base. So they come in pairs. So like angle T and angle R, they share this top base. They're base angles. And angle P and angle A, they share this bottom base. So those are our pairs of base angles. All right, so we're going to focus on isosceles trapezoids. And in order to do that, I'm going to show you another one of these sketches and just stress again for you the importance of understanding the symmetry of an isosceles trapezoid. So the green one up here in the top left is just a straight up normal trapezoid. It's got its pair of parallel sides and that's it. Nothing else special about it. But an isosceles trapezoid has congruent legs. And watch what happens. If I try to make this right side congruent to the left, you'll notice that it starts to look symmetrical. And it is in fact symmetrical. And just like that last kite, if I were to draw a vertical line right down the middle of this trapezoid, I'd be able to fold it right on top of itself. And because of that, we can think about these properties of an isosceles trapezoid and just use symmetry to think about it. So look at angle H lays right on top of K and I right on J. Well, then we can assume that angle H would be congruent to angle K and angle I would be congruent to angle J. That's exactly what these markings show us. These are pairs of base angles. So that's that first theorem, is that the base angles of an isosceles trapezoid must be congruent. H is congruent to K and I is congruent to J. The other thing is that if I were to draw the diagonals, which I'm going to show you here, you'll notice because of symmetry, those would need to be congruent as well. So those are the two theorems about trapezoids. First, the base angles are congruent. So here's my trapezoid. So that means that angle TPA will be congruent to angle RAP. And then these other base angles will be congruent. Angle PTR would be congruent, oops, not triangle, to angle TRA. And then the second thing I showed you based on that symmetry is that the diagonals would need to be congruent. So that means that segment TA will be congruent to segment RP. All right, you guys. And so the next thing I was going to do is going to just do a quick run through that proof. I'm not going to fill this in because I just want to save time, but I'm just going to show you why the diagonals would have to be congruent, okay? And so I just want to make sure there's enough time to look at the next examples. But look, if I were to separate these overlapping triangles that are in this trapezoid, so R, T, P, and then this is T, P, A. Notice, if this triangle was trapezoid was isosceles, then the legs would be congruent. Both of those two triangles share this side. And also, I just showed you that if it was isosceles, the base angles would be congruent to each other. So I could show that these two triangles that were overlapping are congruent by side angle side, which would then make the diagonals congruent to each other. But we don't have time for the full proof, but no big deal. All right, and the last thing, guys, why don't you pause right here, try drawing these, and then check your answers with me. All right, here you go. Welcome back. I hope you paused. All right, so let's just draw sketches of these, make sure we understand. Isosceles trapezoid. So first, I'm going to draw a quick rough sketch. Doesn't matter how ugly it is, because I'm going to mark it with parallel sides and congruent legs. And it needs to have legs QR and ST. So here we go. QR, ST. Even though it's not pretty, because I marked it, I know it's an isosceles trapezoid with the given legs. A kite. So I'm going to start by drawing my kite. Again, I know I suck at drawing straight lines on this thing, but check it out. Here's my kite. And it says the vertex angles need to be A, B, C. So look, A, B, C, vertex angle between the congruent sides. And then angle ADC. There we have it. And then the last one here is trapezoid. Doesn't say it needs to be isosceles, so I won't mark it as such. With bases QR and ST. Here we go. Bases are the parallel sides. There you have it. All right, guys. That's it. Good luck on the assignment. Let me know if you need anything.